Live now. What's going on, everyone? Also, I'm going to be eating some food today as we do some work. In fact, let me try something out here. Let me duplicate this. We're going to do some little stuff before we get into it. Cam only. Yep, and then we have this. So we have cam only here. And then I can disable the display capture and instead have this DSLR camera be the main one. Nice. And I can swap between these guys as we see fit. And then it shows that we're offline. I'm not sure why that's the case. Hotspot's on. The hotspot is on right now, and I'm not sure if it's actually live or not. Which kind of sucks, actually. Maybe I can't stream from a mobile hotspot. If that's the case, that would really suck. That would really, really suck. And I'm not seeing any live. It says scheduled, but oh no, it shows live at the park. And I'm not sure why this is not cooperating with me. Let me check something out. Let's check out Restream.io before. And it's kind of a weird stream. This is a test stream today. I just want to see if I'm able to even do programming work at all at the park or out and about through streaming. I think I should be able to. It seems like it's working fine. So if that's the case, I think we might be good to go. Let me also get some food before we get into it. So today, it's going to be kind of interesting day. Now work on Messy Mansion stuff. Today we're going to be working on actually implementing this engine. Doing some engine coding today. So I figured, for a test stream, why not work on something experimental, right? Sorry, I haven't had anything to eat today. Pardon me. I'm gonna check my stream progress. So far, the upload kilobits per second look good, which is good. And if everything else seems to go as intended, I may start jumping into this soon. So, very odd setup, very different setup. Lighting situation not ideal, but hey, we're outside. This is nature, right? And it's windy. I don't know why it's windy now. It wasn't windy before, but oh well. That's the price for going out in nature, right? That's the price for actually engaging in nature. That's some good food, man. That's some good food, man. One second. So I'm gonna wait a little bit more and check to make sure that frames per second seem to be good. And make sure that everything seems to be running as intended here. And if everything is good, reconnection successful. Okay, we're back. Drop some frames though. Dropping some frames. Dropping some frames. It's okay. Sheesh. It's growing more and more. That sucks. Okay, we're starting to get up though. Back to 2000 kilobits per second. So not the most consistent. Maybe I might have to get something to actually do streaming through my laptop. Periodically, which sucks. Okay, we're reconnected again. Alright, I can't wait to see how this looks in the stream later. I'm gonna look at the VOD and see how well does this actually work. Let me also go on. Oh my goodness, what was that? Let me go on YouTube as well, just to be able to see what's happening here. Let's look at Task Manager, because it shouldn't be having weird behavior like that. 44% CPU utilization just from OBS. 47.6% memory utilization. That's probably due to Superfetch though, hogging all the RAM. Alright. Let me go to here. Let's monitor how this is working. Cool. So I think it should be going fine. Okay. Well, I'm gonna log into Miro and then we'll get into it. Yep, we're gonna use my company email. Yes, it's me. Yes, it's this. Perfect. Good to go now. And then I should be able to log in. There we go. Should be logging in now. Just from opening Sea Lion. That's crazy. That's crazy CPU utilization. That's okay. Let's see here. Okay, back to normal percentages. So I'm going to switch over to try display. And we should be able to see everything here now. So, wow, what happened here? Why are we broken? Why is this not happy? Reload, CMake project. Why are we not happy? What have I done to you to make you angry, code? Well, let's see if I can just run it. It should still compile fine and have no issues. So, as we talked about last stream, there's some weird issues you encounter when writing a game engine from scratch, right? One of the issues is how do you make your code execute consistently across multiple different types of machines? Because some machines might run slower, some machines might run faster. It's a tricky business, right? You want your game to execute, or at least you want your game to appear like it's running consistently across all different platforms. And there's two ways of going about it. At least two main ones that I know about. Maybe there's some other third option that I'm just not aware of because it's a skill issue. So the first one that's pretty common is using something called delta time. And that's taking the amount of time that elapsed from your last frame versus the current frame. And then using that to multiply against all your different mathematical operations you're doing, right? So let's say even a simple example here. Let's say that you're making your character move at a certain velocity every single frame, right? So with using delta time to actually do that kind of calculation, what you would do is have the velocity still for that object's movement, but then you'd multiply by delta time. So that if your frames are updating really quickly and they only take a small amount of time, there should be a proportionately small amount of change that happens to that velocity, or have that velocity only be done. So if you've done like, so let's say, for example, right, you have like, we're operating at 10 frames per second, and your character has a velocity of 10 meters per second. Well, if you're executing at 10 frames per second, instead of moving 10 meters every frame, your character should actually just move like 1 meter instead of 10 meters. And that's kind of the example of how delta time works in this context. So that's one option, delta time. I implemented that initially for this engine, and I was still having this weird issue where it doesn't work consistently across it. But I decided to implement a different approach to this, partly just out of curiosity, and partly just to see, because I think it should work better, in all honesty. But the other option is actually to do something called a fixed time update, where you say, hey, no matter how fast your computer is, or how strong it is, we're going to institute that you work or run at a set frames per second. So in this case, we're setting a limit where every single frame we're going to take 1/60th of a second. We're going to operate at 60 frames per second to do our game logic. Doesn't matter how beefy your computer is. If your computer can complete all the execution it needs to do within a frame, per frame within, I don't know, 250th of a second, we still make it wait the rest of the duration of 1/60th of a second, so that all the updates work consistently. The reason I kind of like this approach more than delta time, I mean, there's different pros and cons for it, and there's different places where you use delta time versus fixed time update. The reason I like this is that the math becomes very simple for your game. If you want your player to move at a certain velocity, you just set the velocity and apply that change over frame. So in a place like here, let's see where we're actually doing some stuff. Let's go to right here. So in this place, before I'd have to do the position of the player plus velocity times delta time. But here, there's no delta time coefficient that you have to be multiplying against. What you're doing is exactly what you intended to do. And that's pretty nice. It's very convenient from a game logic writing point perspective. However, there's also some weird complexities that arise from trying to implement a fixed update implementation. Delicious. Scrumptious even. So, some weird stuff that emerges is the fact that, let's talk about this example here. Let's actually talk about this. So I'm going to stop this play cycle. I'm going to stop this play cycle. We're going to switch to... We're actually going to look through the log. Or actually, let's go through Miro first so I can describe what I'm talking about here. Hopefully it loads. Sad. No one's showing up today. Sad. That's alright. Test stream anyways. Oh well. No one's showing up today. That's alright. Test stream anyways. Anyways. So, let's actually go Miro, so I can explain this problem space. One second. Let's wait for it to load. Okay. So here we have an example of what I was talking about. So let's say we're trying to operate with a frame rate of 1 frame per second, which is really, really slow, but it's for illustration purposes, right? So we're trying to run and write a game that runs at 1 frame per second. And let's say to actually execute all the game logic that we have implemented in the code, only takes 0.1 seconds to execute. Well, if we want to make sure and enforce that we have that same 1 frame per second, we have to wait 0.9 seconds. And let's say to actually execute all the game logic that we have implemented in the code, only takes 0.1 seconds to execute. Are we back yet? We're back. So going back to this. Our ability to wait for a thread is not consistent. So here we might be saying, hey, the game executed in 0.1 second and we just need to wait 0.9 second. That's thread sleeps. That's not the case. Because your operating system can't guarantee that. Our operating systems are not real-time operating systems. Instead, operating systems are typically multitasking at all times, always working across different applications, right? Which means that your thread for your game might come out of focus, might change, whatever. And not only that, even the implementation of how you sleep your thread changes. So in the case of Windows, there's actually no guarantee your thread is going to sleep them as much as you intended to. So over here, if we go into this game function, we go into game and look at the logic that's going on here. At some point, you're going to see, okay, we have our intended wait time. And then at some point in here, we go, hey, we do this thread, sleep for, and then the amount of time we're expecting to wait for. This is this value over here. This guy here, the time that's left over. However, in practice, when we call thread sleep for, you're seeing this discrepancy that's pretty crazy. So over here in the bottom, you see this log, and there's one entry here that says intended wait in microseconds versus the actual. So here, I requested for the operating system to sleep for 8,200 microseconds, right? But in actuality, we're waiting for 25,000 microseconds. So that's the first thing. Sleeping threads in C++, or it's general, on Windows, the number you provide to sleep for is only a minimum. It can actually sleep for more than that amount. So it's almost more like a suggestion. Not only that, depending on how small your wait request is, it may actually sleep for less than you intended to. That seems to be less of a problem or likelihood. Biggest thing is it waiting longer than we want it to. One second. I got some sauce on it. So, how do we deal with this? Because it seems like a violation of our trust between the coder and the operating system, right? The fact that we have this thing that we can't really guarantee. Well, that's the problem we're trying to figure out today, right? The fact that we have this thing that we can't really guarantee. Well, that's the problem we're trying to figure out today. So, there's one idea I have where we can actually, instead of waiting for this amount of time, wait for time. Hey, what's up, Fife? How you doing, 5X? Glad to have you here. Hopefully the audio is still intelligible. This is the first time I'm doing a stream outside, so let me know what the issues are, if any issues that you encounter or see here. We're gonna be figuring it out. Today's kind of a test stream, and using a mic here to try to a little lavalier. Okay, but yeah. So the first iteration idea is, okay, we can try sleeping for smaller amounts and then measuring the amount of time that's elapsed, which we're kind of already doing here, and then see if the total elapsed time in microseconds meets or exceeds the intended wait time we had in mind here. So that's one option. It stuttered a bit. Yeah, it's a bit shoddy. I'm using my mobile hotspot to do the streaming today. So we're using the mobile hotspot today to try to do the streaming, but I might have to upgrade or something if I want to do it more often outside, which I kind of do, in all honesty. It's kind of nice being outside in the world, touching grass. Anyways, I'm not sure what time we came in, so if you want, I can go through what we're trying to do here today. Oh, air? Alright. The dang air. It wasn't even that airy today, but in fact, 1 second. Let's try this out. I don't like having it on my mic. You like the water in the background? I'm glad. Yeah, it's also nice scenery too. Like we have a lake back here. It's a large park. It's very nice. Anyways, so I guess I can re-explain some stuff if that would be helpful before actually tackling this. But also, my bad, camera went out and I didn't hear it. What can I say? Amateur hour, guys. Amateur hour. What can I say? It's how it is. Yeah, now you can see the actual park here. Very nice. And yeah, but that's the whole goal. It's to be very chill, have a very chill atmosphere. Just coding engines in a nice, peaceful place. Anyways, less peaceful is programming. So let me recap exactly what we're dealing with here. So we have this game engine that I've been working on for a little bit, and it's pretty good. But I started doing some changes. Less peaceful is programming.